So, again, good afternoon all. This is the third session on principles of extractive metallurgy. So, in last few sessions, we have discussed a very basic introduction like what is ore, mineral, gang, and so on and so forth. Then we came to first we gave our introduction to yeah, we started with mining, right? Sir has started with mining. So then we came to ores. So there we discussed minerals, gang, few different terms, few important terms, and then we defined our process or operations, you can say. So then we first initially begin with our unit operations, right? So then we did the initial process like mineral beneficiation. So mineral beneficiation involves mostly you do not change the chemical property of your ore or the valuable mineral in your ore. You just change we just play with the physical properties. Like, so for example, we have seen magnetic separation, mineral beneficiation, like froth flotation. We used like sedimentation. Then we used sorting. So there were different ways, and we also introduced a process at first called comminution, right? So what does this combination tells us about? The combination tells us about how we reduce our powder particle size, right? How do you reduce your size of your ore? We get lumps, and then we have different jaw crushers actually. So then we do use different jaw crushers, and then we use grinders to reduce the particle size further. And after that, we introduced a different process like unit operations, right? So we introduced a pre-treatment, you can call it as a pre-treatment process, where we want to lessen the burden on the upcoming process, so that on totally you are making your process more efficient. You are separating gang materials as much as possible at first. So at first we had um, sedimentation, centrifugation, and froth flotation, magnetic separation, electrostatic separation, and there is a density separation. So we have used different types, right? Yeah. So after that, so what are we going to do? Now there is this other term called sorting. So before involving going into any process, what if we can sort out the, like, sorting is nothing but you are separating, you can say, most of it. So you are separating some unwanted gang minerals that you do not want to go into your process, right? So that's what we are going to do here in this lecture. So we will first do the sorting, then we go to the yeah, after sorting, after sorting we will go to the solid liquid separation. I mean, what after your mineral beneficiation process, you're mostly left with, if you're dealing with hydrometallurgy, you are left with liquid, right? You want to separate that liquid, and after that, to undergo into any further hydrometallurgical parametallurgical process, you further need to they have a strict input of powder particle size. So then how do you measure that powder particle size or particle size? Then there are fuels. What are the type of fuels that you are going to use to, for example, if you are doing a parametallurgy, how you are going to introduce energy, right? You need either fuels, or if you're doing electrical energy, then again you need electrical energy. Electrical energy also comes from fuels. So if you're talking about uh, like thermal energy to electrical energy, like burning coal, superheated steam, this steam will turn your turbines, and then it will happen. So, and then we will discuss a little bit about the calorific values of these fuels. How do we, like, even in fuels we distinguish depending upon the amount of energy it will give per volume, right? So per volume or per kg, per kilogram, it depends. Now before going into all to that, let's see what sorting is. Sorting is mostly told as a separating process. So it can be ejected. So there is this ejection happening. That means unwanted, right? So unwanted materials are gone away. Either by it can be happen by mechanical, electrical, or hydraulic or pneumatic process, right? Initially, people were trying to do the hand sorting, but sorting depends mostly upon if there is a very physical distinction. If you are doing some hand sorting, right? If you can clearly distinguish between and they're separated also, right? Then only you can just pick it by your hand and throw it away. So that is one thing that is called hand sorting, right? So now the main thing that comes is the detection. Now how you are going to do detection? So that's where comes the sensors. So these are called sensor based sorting. So or you can say what type of material you're sorting. If you call it as a ore, then you call it as sensor based ore sorting. So now these sensors should get some signal, right? So they throw some signal, and the signal again comes back via some response. So that response depends upon your material, right? So for example, this is your conveyor belt that is moving, and you have material here, right? And then you have sensor here, right? So you throw some signal, and the material will take up signal and react to it, and it throws back. So that's what happened, right? Every sensor works on this principle. So it throws something, and it get back something in a response. So depending upon the type of response, you have different types of sensors. So uh, starting from, if we are talking about from layman terms, so let's say you have density, or you can call it as atomic density. Whenever you talk about atomic density, that means we are talking about fingerprints of elements, right? So whenever you talk about fingerprints, then you get characteristics. So characteristic means characteristic wavelength, and characteristic wavelength indirectly tells you the X-rays. So we use X-rays for that. And if we are dealing with, if you want to know the composition, again you can deal with X-rays, but not characteristic. Yeah, characteristic, but the content characteristics and continuous spectrum, which comes from XRF, the fluorescence. So it takes, for example, you throw one wavelength, and it gives a different wavelength, right? So each atom will give different wavelength. Again, that is also one type of fingerprint for you. So that's how we know what type of element, and depending upon the counts per area, we will define our composition. So that is our XRF. And if there is a visual fluorescence, right? So if there is a visual fluorescence, then we call it as a X-ray luminescence. Okay, so that is one thing, and we can even use the color. It depends upon transmittance, reflectance, and the brightness, right? These are different things that I can define. And if you are talking about some gamma rays, then you are talking about radioactivity. So radioactivity is nothing but some atoms are like they are dying, in very layman terms, not dying, but they are undergoing some fission reaction. So during those fission reaction, they will emit gamma rays. So that's how you know which type of material is there, or which type of elements are there. So depending upon those things, you need to buy as sensors, right? So that's how sorting works. And sorting also needs a strict initial processing, because you cannot throw, for example, uh, if I want to separate two phases, okay? So if I take very big particle, then these phases may be interlocked, right? That's what we studied in previous session, the locking, interlocking, right? So if you don't break this, these phases will not get separated. So there is some strict things that needs to be considered whenever you are trying to do the sorting. Okay, so that is one thing. And again, the operating costs are large if you are involving some, again, pre-treatment process, right? So yeah, that is about that. And so again, these sorters need these sensors, right? Again, they are not cheap, they are expensive. So again, they are expensive to operate, and you cannot do for small things, okay, the small batches. You need to do it for big batches, so that it is accommodable, right? And also, if you have very fine feed, then at is if you have very large, large lumps of ore, then at is then that is not very fit for sorting. And if you have wearable ore, so for example, one time I gave a ore which contains 60% of aluminum. One times I put an ore which has 20% of aluminum. Again, that is not good. So wearable ore is not good. So again, the sorting, if you have very fine feed, again that is not also good for sorting, right? Now, that is about sorting. So there are many different types of separation methods that we follow in industry. So gravity separation methods are used, right? We have seen last class, and then we have electric separation method, free fall, high tension separators. So these are there, wet magnetic separators, dry magnetic separators. So in dry magnetic separators, again you have low field, high field, low intensity, high intensity. So there are different types, right? So I'm not going to discuss all those because sir has already covered. So in this, now moving on to the next one. So once you got so once you did, for example, you are carrying a hydrometallurgy process, right? So for example, we are dealing uh, beneficiation process, right? Or we are doing hydrometallurgical process, pre-treatment, we are leaching or dissolving something. Then most of these processes are remained with water, right? And in that you have your ores. Or even if you're not talking about water, let's say we have some chemicals in which we have our ores, right? For example, if I'm taking fourth rotation process in which you will get a foam, you just collect it, right? Now how do we separate them, right? So for them to be separated, either, so for example, if I have a this is my container, and in this container I have my ore particles, right? And it is filled with some medium. Now what I'm trying to do, I'm trying to separate them, right? These guys from the liquid medium or fluid medium. Now how do I do that, right? So to do that, either I do sedimentation, and we know sedimentation is nothing but you just leave it, that medium, for certain amount of time, and gravity plays its role, right? So what does it do? It makes the particles to come down, right? It makes sure the particles come down, and the liquid, like, it is less dense, so it floats up. So that's what happens here. Now, for a particle to come down, what are the factors that depends? You have discussed this many times. Again, I'm going to say it. So you have gravity. This is the dominant one. So it does its part. Now, when something is moving in a liquid, you have your drag force, and there is also something in some medium. You have your buoyancy, right? So gravity must be greater than drag plus buoyancy. Then only it will start settling. If it is equal, then it will just stay there. If it is very much like gravity is less weaker than your drag and buoyancy force, then if buoyancy force is very large, then you can say your particle floats up, right? So that's what we learned from uh, fluid statics, right? Fluid statics tells you that. So if gravity is greater than your buoyancy force, then it will sink. If gravity equals to buoyancy force, then your particle will stay, right? If your gravity is very much less than your buoyancy force, then particle floats, right? So that's what we learned from fluid statics. Now if something is moving, you will get another force, that is a drag force. Okay, so we even call the sedimentation as a thickening, right? Sedimentation, this is what we are talking about, or you can call it as a thickening process. Yeah. So and this settling rates of particles in fluid are governed by people who have tried to different laws. So there are Stokes and Newton's law, which again we have discussed. Stokes law is for Reynolds number less than 1. Newton's law is for Reynolds number greater than 1. If you have turbulent flow, then you use Reynolds number. sorry, you use Newton's drag force, or if it is less than Reynolds number is that one, then you use Stokes law. So again, very we know that settling velocity, it depends upon your size power m, right, from the equations that we have derived. So, and also it depends upon density. So for now the density is constant, right? So higher I mean the if size is very small, then your settling velocity also is very small. So gravity will, even though the gravity acts, but it doesn't have very much prominent effect on your first velocity, right? So the small velocity, the small size, so here density is fixed, so the small size particles will settle very slow. It takes large amount of time. So what do we do then? To settle them, we change the characteristics, right? Either you increase the size or you change the surface as that they try to agglomerate, right? So to change the size, we cannot inherently change the size, right? It is not a balloon, so we just pump air, it will be like big, no, right? So they are dense particles. For them to settle fast, what if they get attached to each other, right? You can call it as agglomeration. Then your effective size is increased, right? So if your effective size get increased, then you can say, then your settling velocity will also increase. So now how do we do that? So to get there are two ways. Either you coagulate, or you can say, uh, which we got it in previous assignments, which is flocculate, right? So these two are there. Now let's talk about coagulation first. So coagulation, what happens in coagulation? It's more like an agglomeration, so where fine particles come close together and they attach. So for the surface forces to be dominant, then you say it is whether it is a van der Waals forces or London van der Waals forces, right? So these forces must be dominant. Now, and we know this very much. I mean, even J it is very famous. So A by R power n minus B by R power m. So it is like the potential energy between the two atoms, right? So now force, you just do differentiation with respect to R. So it will use a force between two particles, right? Now when you do that, when you draw this diagram, it will look like this. Okay. It actually look like this, right? So this is your potential energy, and here is your distance between them. Now, if they are very far apart, there is some attraction, right? Because of electron cloud and nucleus, there is attraction between them. If you are talking about two atoms, let's just talk about two atoms, okay? If they are very far apart, then there is this electron nucleus interaction, electron proton interaction, so which attract each other. So that's why the potential energy is negative. And then once you reach certain distance, and at this r, the critical radius r, right? Now if I draw the force F equals to minus du by dr, then you will have the graphs of different, right? So at first, this r, you have minimum potential energy. Minimum potential energy means minimum potential, that means that they are stable. So at this position you will have your bond length. This is your half of your bond length, right? And when they again come closer, the potential energy shoots up. Why? Because now there is a proton proton interaction. So that's why you cannot fuse two atoms very easily. So you need very high amount of energy. That's what happened in nuclear fusion. So again, it only happens for hydrogen and small atoms. So you cannot fuse iron like big atoms, right? It's really much not possible for now. Maybe people may try it later, because that's what it happens in universe, right? It happens in sun. That's how the stars collapse. where at first the hydrogen starts become helium, and then you have helium becoming lithium, and then this process goes on to certain extent, and finally there is this red dwarf or huge giant. Let's not go into that. That's what happens in star. So yeah, now this is our layer. So yeah, and for some particles may not adhere each other, right, very much effectively. So to do that, and some particles may have charge. So for example, if some particles are negatively charged, then they repel each other, right? Negative charge, they repel each other. So distance is large. Now what we are trying to do is we are trying to alter their surface such that we add something of different charge, they attract to this guy. Now we make sure that the total charge is neutral, so they start attracting. Now we have the wonderful attraction coming into place. So that's how it happens. Now, what we use coagulants. Now what are coagulants? Coagulants are mostly electrolytes with they have which have opposite charge, and they go into when we add into solution, they go and stick to the particle size, and they neutralize the charge, and allow the particles to come in contact, which results in adherence, which is because of the molecular forces. Now, and this type of coagulation can be achieved by adding inorganic compounds, or you can even add organic coagulants which contains polymers. See, now this is about coagulation, and when coming into this coagulation theory, so what happens is, so if suppose this is your surface, right, and suppose I have add some charges, inorganic charges, right, so it has a negative charge, so this become positive, and finally you will have, and finally they get attracted, right. So now, because of this attraction, so this happens while the particles are in motion, right. So when this surface move, they get attached, so they also starts to move, right. They also starts to move. So there is this layer up to which, then after this, okay, so now, and they are very strongly adherent, so they are very prominent, so when this moves, they also moves. But what about the next layer? So that layer is not very much attracted to this guy. So then what happens, then there is a shear. So that's what happens in fluid flowing on a flat plate, right. So when the fluid is moving, so the fluid just, I mean, near to the surface has zero velocity, but so that is what happens in pipe, right. So this is the velocity vector look, right. Suppose if a fluid is flowing inside a tube, then this is how your fluid looks like. The velocity distribution vector looks like. At at the surface, because the velocity fluid layer and these are constant, so they are not moving, right. They are like uh, if you apply the friction or drag, then you can say the fluid just above the surface is zero, that is not moving. And what about the next layer? It moves a little bit, and there is a shear between these fluid layers, right. So that's why when you represent fluid vector, or fluid vector of this thing, then you will find the different vectors, the tensor vector, right. You will find shear forces also here. So that's why when you write the equation, so to find any fluid dynamic property, you will find this equation, right, Navier-Stokes equation, which involves your so many forces, right. You will have your gravity forces, you will have shear forces, and then you have momentum also. So that is about that. Now, the layer above this layer, after the, and see, sorry, the layer which is attached to your surface, that is called as a bound layer. That is bound layer, and the layer next to the bound layer is called diffusion layer. and then you have bulk solution, right? So whenever this layer moves, this layer also will move. But when this layer moves, there is difference in velocities between this guy. Let's say this is v1, this is v2, and v1 is greater than v2. Whenever this happens, there is a shear, right? So someone, a layer, is moving upon a layer, right? So this is your metal surface. Oh, sorry, not surface, surface, right? So your mineral or particle, you can take it as, right? So this is your particle surface. This is your bound layer, and this is your diffusion layer, right? So whenever this happens, there is this shear. This guy is moving this side, and this guy is trying to stay. So that's why you will have a shear stress or shear forces, tau, right? So because of that, and that layer, right, and the potential at that layer is called as zeta potential. And people even call it as a plane of shear, right? Because on that plane, the shear is happening, right? So it is happening like this, it's happening like this. On that plane it is shearing, and that plane is called as, and the potential of that plane is called as zeta potential. And for ideal coagulation, the potential at zeta should be zero. That means at once the coagulants are getting attached, the whole charge is getting neutralized. So if you add more number of coagulants, then the charge will shift to negative. So again, that is not good. If you have less, then the charge is not neutralized. If you add more, then the charge is over neutralized. That means the extra charge is remaining, and so it should be such that the zeta potential should be zero. Then only you will have a good coagulation. Right, now moving on to flocculation. So in flocculation, it is more dispersed rather than the dense packing of, not, I shouldn't say, yeah, you can say dense packing of particles close to each other because of coagulation. But flocculation, you will see there is no dense packing because you are adding the polymers, long chain. So you functionalize this polymer chains such that at some positions you have cations or anions. Cations or anions. That means you are functionalizing your polymer. So now this polymer has charge. Now what happens is, so because of this charge, your particles will get attracted to it. So it's more like, for example, you have your polymer like this, and the particles are like this. Okay. So this is what happens. It is more like open structure. Rather than closed structure when we see what we see in coagulation. Okay, so that is mostly about flocculation. So there are different examples. You have polyvinyl phosphate, which is anionic, and polyglycidyl tributyl phosphonic chloride, which is again cationic. There are some polyacrylamides also, acrylamides, which are non-ionic, but you we can make them functionalized by adding changing pH. You can change the structure also. So yeah, so that is about flocculation. Now, why we have changed the properties. Now there are different ways you can separate, right? Now how do we separate them? Now there are certain equipments which we used, such for during instead of sedimentation we can use centrifugal forces, where you use centrifugal force, or which is mv square by r, which is centripetal or centrifugal force. When they are not balanced, then we do not equate those terms, right? So we use the circular forces. When body is moving in circular motion, there are some forces acting on it. So we use that to separate them, right? And there are different ways people do it, you know. There are some conventional high rate, so high density, and depending upon your properties of these mineral particles that we are using, we use different types of processes. Okay, So that is about that. And now the other thing is, you separate by applying some external pressure, right? So either you apply pressure, that means you apply force, you apply positive force, or you apply negative forces. uh, I shouldn't, it's not direct way of saying negative forces, it's nothing but you are using low force, right? Not even low forces. So why I'm saying negative forces is because you are creating vacuum. So that's why I told negative forces, which is not which shouldn't be like in a direct term. It is just for layman understanding. Okay. So there is some pressure in fluid. You are applying extra pressure such that they move. Okay. They You are pressing them against some layer which has some porous structure. So only liquid can pass through, right? So not the solid particles. So that is one thing. And there are different types of filters which we have even used in syringe filters also to like to filter the gig whenever uh, people have seen this in hospitals, right? There is this a bottle which contains your medicine, right? So whenever you are prescribed with injection, right, syringe, so then the nurse will break or doctor will break this. So whenever glass breaks, it will not break perfectly, right, because it is a brittle. So most of very fine particles can go into your medicine, which is very dangerous when we talk about. So they can be very fine, you cannot even detect them. So that what we do is we first, so what we do is we first take out the solution, then we pass it through a filter. Okay, this can be a 0.2 micron filter. Okay, it's more like so 200 nanometers. So the hole is 200 nanometers. So you pass through the solution or pass through your medicine through this. So you apply pressure here. So this is your syringe. You attach this. So you apply pressure to the solution. Now you it passes through this. So any type of impurities or like glass or very small particles that have fallen through, they can be separated, and you have a solution, I mean glass free solution. So that's what a common practice is. Okay. And to avoid that, now there are these rubber stoppers. So you have this bottle and it is made up of glass, but not this guy, the top portion. It is made up of a very high density plastics. Okay. So then you just insert your syringe and take out the solution. So that's what the common practice is now, to avoid this unnecessary extra work. So that's what we use here also. So we apply pressure. So there are horizontal filters. We apply air pressure. So for example, you have a solution, and so not solution, you have some slurry, right? So slurry is nothing but a mixture of solid plus fluid, right? It can be liquid or gas. So in metallurgical basis, we only talk about liquids. So let's add liquid. Now this is a slurry. So you have your solid. Solid is nothing but your mineral, right, or ore, and the liquid is nothing but in which you have suspended. Now, now you apply pressure here. They pass through some filters, right, and this filter will make sure only liquid is allowed, and the slurry will remain as it is. And there are vacuum filters also. There are mechanical waste pressure tube press also, which uses a mechanical pressure. So we call it as a tube press. And then we apply vacuum. There are different batch filters, continuous filters. So in batch filters you will have leaf filters or tray filters, and in continuous filters you have rotatory drum and disc filters. You can just look up through, and you can go through the mechanism also how they follow. The basic mechanism is this. The basic principle behind is this: you apply pressure, someone goes through, someone will not, right? So that is about that. And then you finally dry them, right? You apply heat energy, right? So there are different types of dryers. There are hearths, grates, shafts, fluidized bed. So fluidized bed is nothing but you you have a bed, a loosely packed bed. Somehow, let's say the powder particles. You just put some powder particles here. Now what you do is you apply air from bottom, hot air, such that these particles will float, and these solid particles will behave like a fluid particles. Then you called as a fully developed fluidized bed, right? And there is this flash process. Flash process is nothing but it is a counter current process. So from top you are throwing something, like you are distributing the powder in a certain way, okay, or you are spraying powder. Then and from bottom you are blasting air, right? So it is more like a counter current process. So powder is coming down, but the air is going up. So it happens in seconds. So that's why we call it as a flash. And there is this flash melting, flash reduction, flash oxidation. There are different types that we do. So which will come into picture when we go on through the next sessions. Okay, right? So it happens within seconds. So that's why we call it as a flash. And there is a hearth. So hearth uses air from burning the fuel. Same goes for shaft, which rotates. So that's it. So that's what about the drying, right? Now coming to this calculations, right? The slurry. So so we have few examples in the assignment. So let's solve them. So we know a slurry contains the suspension of solid in your liquid. Okay. So the concentration of your solid percentage will be equals to what? Mass of solid in your slurry divided by, again, mass of solid plus mass of liquid, or you can directly write it as mass of slurry. Now let's define the densities also. This is for solid, this is for liquid, and this is for slurry, right? So you can write it like this, right? So for example, let's take 100 kg of slurry. 100 kg of slurry. Then mass of slurry will be solid. Let's take mass of solid as S. So if I am talking about 100 kgs, then mass of solid will be S, and mass of liquid will be 100 minus S. Right. So mass of solid and mass of liquid is 100 minus S. Then what is the volume of solid? So that will be equals to S upon rho S. Then volume of liquid 100 minus S upon rho L. Right. Now then what is the volume fraction? Volume fraction of solid will be equals to S upon rho S divided by, now let's take mass of slurry divided by density of slurry. Same goes for liquid, 100 minus S upon rho L divided by mass of slurry divided by density of slurry, right? So this is about their volume fractions. Now let's move on to if okay so let's move on to the percentage of if you want to know the volume fraction of solid, you have your solid divided by solid mass divided by density of solid, okay, and the whole that is divided by the whole divided by mass of slurry by density of slurry, right? Now so mass of slurry, which is equals to weight of uh, solid plus 100 minus S is weight of solid, this is weight of liquid, right? So this we know, right? Now if the question is, if they ask what is a flow rate, right, what is the volumetric flow rate, and how do we define volumetric flow rate? Let's say that is defined as a, okay, so flow rate is given in terms of meter cube per second, and here we use meter cube per hour, okay. Now, if I'm talking about mass flow rate, then it is represented as like this. The mass flow rate is nothing but we represent as m dot, so it can be written, so the units are kg per hour, right? Then what do I need? You multiply mass flow rate with the density of your slurry, that will give you mass flow rate. Now if I want to know the mass flow rate of solid in a slurry, then what you do, this is m, this is the flow rate times sky into the weight or the percentage of solid in your slurry. This will give you the final result, right? And you just do some this simple mathematical jugglery, okay. So use 1 and 2, you will finally remind with percentage of S will be equals to 100 times density of solid minus density of slurry minus density of liquid upon density of slurry minus density of liquid, okay. This is the percentage of solid in your slurry. Now you substitute here, the mass will be equals to flow rate into density of slurry times 100 rho S SL slurry minus flow liquid upon, it's cancelled. You finally have F into this guy, okay. So this is the total mass flow rate. Now if someone gives you the density of slurry, let's say density of slurry is 1000 will be water, right? Not even meter cube. Let's take 2000, okay? 2000 kg per meter cube, and density of your density of your solid will be equals to 4000 kg per meter cube. Now calculate the percent solids by weight present in your slurry. So what is the amount of solid that is present in your slurry? So if you want to know that, now how do we do, right? So we know so let's assume our slurry is made up of water, right? So I'm just taking random numbers, okay? So there's no need to get confused too much. I'm just taking random numbers. So let's take our density of liquid is 1000 kg per meter, which is water. Now, what is my percentage of S? Will be equals to 100 into what is rho S? 4000 times slurry is 2000 minus 1000 upon again rho SL 2000 divided by what is rho S? 4000 minus 1000. So everything goes, it will 200 times this will become 1000 divided by 3000. Okay, so solid is 33.34 kgs. Oh, sorry, percentage, right? This percent. Now, if you want to know the mass flow rate, if he asks, let's say, the mass flow rate of your slurry, right, is, let's say your mass flow rate is 0.5 meter cube per hour. Now you know density of slurry, which is 2000, and also you know the percentage of S, 33.34. Then what is the mass flow rate of your solid in your slurry, which is m dash, which is equals to 0.5 into 2000 into 33.34, which will be equals to, so one goes 200 times 33.34, so 6668 kg per hour is how much we get, right? So that's all. Okay, so this is 33.3 or 33.3. It is we are writing in percentage, right? So it will be 0.3334. So 66.68 kg per hour. So that is our mass flow rate. Now, moving on to the powder particles. Now, how do we measure the powder particles, right? So you divided everything, you dried. Now you need to sort out for the next process. Now you do sorting, right? Pre-treatment, because some process have some rich inputs, right? So now how do you measure the powder particle size? Right, there are many ways to measure the powder particle size, right? So you have the very basic and common methods that has been that is very ancient one also. The people still carry out, even though that is very it doesn't give you a very accurate result, but at average your value is same. So to get very accurate measures, there are different very more advanced methods like DLS, dynamic light scattering, or laser diffraction methods. You have your SEM, where so SEM do not have softwares that directly give powder particle size, right? So what you do is you disperse your powder particle size onto a carbon strip, right? So where they get attached. So let's say this is your powder particles. You dispersed your powder particles on your carbon tape. Now what people try to do is they first do the sieving. So let's first start the sieving process. Instead of going directly to the SCM, let's first deal with the sieving process, okay? So what does sieving has, right? So sieving is nothing but you pass through your powder particles through some holes, okay? Or people call it as a more good way of saying is aperture, right? So you pass through powder particles through aperture. Now there are some standards we follow. So each C will have certain number. There are different types of standards. Okay, so each company will follow. There are few standards, not like a very large amount of standards because people get confused. So there are few standards, and the companies mostly follow one or two standards. That's all. So they give a number, and depending upon that number, so sieve is nothing but a cross grid of wires. Sieve is nothing but a cross grid of wires of a certain shape, and these grids have because of these cross grids you have apertures, right? You have some holes, and these holes have certain size. Now every so standard is nothing but the standard of the sieve is nothing but they each sieve have a certain number. Okay, depending on that number you have your size of this aperture. Okay, and if you have let's say you have a very large number, then that means the number of apertures or number of holes per square inch, right? So it is nothing but number of holes per inch. Okay, so that is what it is, right? It is very oldest method. See, we still follow it, Now the number of holes per inch. Now if you have a very large number, then there are more number of holes per inch. That means your size of your aperture becomes smaller. So there is this relation. That means if your mesh number increases, the size of your aperture or hole decreases, right? Because the number of holes needs to increase per inch, right? And to increase the holes should be increased per inch means that means the size of the at 1 inch you have to accommodate more holes. That means you're decreasing the size, right? So that's what happened here. And there are certain numbers like 200 mesh, 300 mesh, which defines to for example, if I'm talking about 50, or if I'm talking about 200, it resembles to 75. If I'm talking about 300, it might resembles to 120 or 150, right? So there is this what do you call we follow certain rules, so that standards such that this mesh number belongs to this hole. So these holes may not be exactly perfect, but they are mostly at that range. So each company may slightly vary this size, but for example 200 micron, 300 micron might have 75. For one company it may be 75, for one company it may be 76 to 74. So it will not vary that much. Okay, so it's mostly the same. So yeah, you have different sizes of mesh stacked on each other. So these are all put in a machine which vibrates them vertically or horizontally in a certain direction. Okay? So not vertically because of water particles jump out. So horizontally they may vibrate. They give some vibrations. Okay. So the first one will have low mesh number, and from top to bottom there is an increase in mesh number. Okay, that means the size of the aperture goes down, right? And whenever you put your powder particles here, and there is also some standards. Before putting them we just heat it so that there is no moisture on the powder particle surface. So we heat it at 95 degrees centigrade or 105 degrees centigrade for 1 hour mostly. We put it in an oven, right? So that's what we do. So once we get it dried up, we put it on this first sieve or first mesh. Then we start to vibrate. So these the finer particles will go down, and the more finer particles will reach to the bottom. So depending upon the size, if the particles are bigger than your sieve aperture hole, then they will stay there. And now how do we calculate this? How do we calculate the average particle size, right? Now sorry. So how do we calculate the average particle size? Now to do that, we use this method called what is the percentage of weight we retained. Okay, so let's say you have a table. This is your table, and this is your mesh number. This is the percentage of weight retained. Okay, so depending upon, then it is your cumulative, right? So let's say from I'm going from 1 2 3, it's not the mesh numbers. Okay, so let's say I'm going from 30 50, so on and so forth, right? Finally you have like 50, let's say 1200 or 1500. Okay, so let's say here's the number I'm going to follow. So at first I have percentage retained. So at 30, if I'm talking mesh number 30, so I have certain size for this. So for example, for 30, uh, it might be like 500, maybe 500, or mostly 500. Let's say for 50 I'm close to 200 micron. So it follows. Now if something, so at first 30 nothing retained, but at 50 I got 10% of the weight retained, then that means my particle size will lie between these two guys. That means it is greater than 30. Oh sorry, it's not greater than 30. That means it is less than 30 and plus 50, greater than 50. That means it is between 500 micron to 200 micron, right? So it may be 300 micron, it depends upon, right? Let's say it is 200 itself. Okay, so then what happens? The 500 plus 200 will give you 700. 700 by 2 will tell you it is 350 microns. So that means we can say that the particles which we retain above 500 are 350 microns. So again, it is not very exact, but it's we are taking more or less the average value that we have retained. Okay. Now moving on to the next one. So depending upon that, so for example, it may retain 5 8%, and finally there is 100 weight%. We retained everything. Okay. So the cumulative percent will go on and add up to 100%. Right? Sorry, we retain nothing. At one point, nothing comes out. So let's say our powder particle sizes are large. So at one point, we finally reach a cumulative of 100%. Right? We retained everything. Now, how do I calculate the average particle size then? The average particle size will be given as 100 upon summation of weight amount of returned divided by particle size at that mesh. So you add all these guys. So at first you have what is the weight retained. That means the 10%. 10%, for example, if I took 10 grams, then 10% of 10 is 1. So at this guy, right? So 10 divided by, what is my D? D is 350 micron. Then I keep on adding this until wherever I reached our final. So then I do the summation. Then I divide it by 100. Then you finally get the average particle size. Right? So that is a way to get the average particle size. Now, for example, this is we took average for so for example, if you do not want to know average particle size of through hole, I just want to know the average particle size at one point, right? For example, we use 80% pass, that means passing size. That means if some sieve allows 80% of your powder particles, then we use we assume that right. So if you have 80% of passing size, then that means we assume that that is the best way to include into any process. Okay. So how do you get the 100% passing size? So not 80%. You use the reverse, retain. So if you have 20% retained, that means the 80% is passed, right? So we can use that, right? Now, so let's say 80% pass is what we decide. Then we find out which sieve will give me the 20%, and this is my mesh number. Okay, this is my percentage of retained, this is my percentage of passed. So if my so for certain mesh number, let's say this is my mesh number, let's say this is like 200, okay, and the percentage of retained is 20 and the percentage of passed is 80, then it is good, we directly can use that. What about if my percentage of pass is less than 80%? Okay, let's say this is 22. Okay. So if it is greater than 80%, or we can take, right, or it is less than 80%, then what we do, right? So if it is 22 point, so it is 22%, then it will be 78%, right? Then what we do, right? Oh, sorry, this is not 70. This, okay. So let's say it is 78%. So we want above 80%, right? Above 80%. Then if it is 78%, then we need to find what is the average size of our particle, right? Then how do you find the average size? In this range, in between, let's say above 1 you have 100 mesh size, okay, then it has certain aperture size. Let's say this has some aperture size of D2, it has aperture size of D1. So we can directly use this formula, it tells you the average, but we cannot use it if your distribution, if your mesh number and this percentage of passed or cumulative of passing is linear, then you can use this. So what do I mean is, let's say this is my particle size, or the particle size we found, and it is a cumulative. So what are the particle size we found here, right? And it is a cumulative. If it is linear, then you can follow this formula. If it is non-linear, then it, let's say it is something like this, then you have to use this formula, 100 into x by k whole power b. Okay, then your y is cumulative mass percentage or passing size, and x is your screen aperture size k is your size parameter, or tells you the size of your particle, okay, and a is your distribution parameter. So y equals to, now if you apply logarithmic, then log y will be equals to, so log 100, at first you take out constants, then plus a log x plus a log, oh sorry, a log minus k. Right. Now to get these guys, right? So let's say my y is 100. Okay, so everything I'm retaining. Okay, so cumulative percent is 100, right? So then it will become log 100 equals to log 100. These two guys will get cancelled. So then x will be equals to k. So that means it is the maximum size of a particle, right? So that will tell me so distribution parameter gives the range of different sizes, right? So k gives me the measure of the top size where you get 100% retain. Okay, then nothing goes through. And this is your k. Then what is your a? A will tell you the range of different sizes in the sample and the size and the range of different sizes in your sample. Okay, that gives your distribution. So a will define your distribution because that's what it tells, right? The slope. That depends upon distribution. If distribution is linear, parabolic, or any type. Okay. Okay. So that is about sieving. Now, so sieving again is not very. You can say it doesn't give you exact values. So for that, what do we need to do? You can use different process. You can use DLS. So it depends upon dynamic light scattering. So how your powder particles. So if you have a clean medium, let's say you have ethanol, so it has some reflectance transmittance, right? So some light goes through and it comes out. It has some certain scattering property, which is not much because it is mostly transparent fluid, so transparent liquid, so it does not scatter as much as the different particles. Now what I'm trying to do, now I'm trying to introduce some particles. Let's say this is my top view. So this light will get scattered, right? So depending upon this scattering, you have some screen here, and depending upon this scattering, you define your powder particle size. And there are different methods, different formulas that define them. So and then you have laser diffraction also. So you use laser. So it is a strong, it has a very short wavelength, right? And then you bombard with the particle, so it will get diffracted, right? So light diffracts around the small particles. The same goes for the powder particles also. So the laser get diffracted, and depending upon this diffraction pattern, you will understand what is the size of the particle. Again, there are different formulas for this, right? And then there is this virtual way of knowing is using SEM. Now, how do we do this in SEM? So you take a copper tape, which is a conductive tape, right? And because the powder particles are not continuum, right? They are not solid particles, right? There is no continuation. The powder particles will very small and break. So dispersed. So what you do is you disperse your powder particles on to the carbon tape. Okay. Now what you do is now you apply some magnification, right? So for example, maybe 200x, depending upon your size of the particles. If the size is very large, then you need not to go at very high magnification. If your size is in nanometers, nanoparticles, then you need to go like 1 lakh, 2 lakh, depending upon the size. Okay. So let's say there are some big particles. Okay. Now if I want to know, what we do is we first take an image at a certain magnification. Okay. Then we take that image and we put it in a software. So the best software for image processing, we use ImageJ. So people mostly use that. So there is a software called ImageJ software which is available. People can even download the crack version also. So and once you get that image, now you change the contrast, right? So you get one contrast, which is a grayscale. You get the SEM images are mostly in grayscale. So you get the grayscale, and then you change the contrast to some color. So followed by that contrast, you define a shape, a circular shape. It depends if you are doing elliptical, circular. You can define that shape also. Okay. So there are some parameters in your software. So this image software, you define that, and depending upon that input, the image software will find out the particles of certain limitation. Like for example, I have given some ellipse, right? So it has my major axis and minor axis. So I have given some value x and y. Depending upon that value, with some error, it will find of those particles. And if you find those particles, it will count. It will take the area of them. It will find average diameter. Now, the next thing is how to find the average diameter of the particle, right? So there are different ways, and there are arithmetic diameter, geometric diameter. There are different ways. But when it comes to microscopy, we used only two: the ferret's diameter and Martin's diameter. So ferret's diameter will give you the size of the particle aligned in certain direction, and you draw. So let's say my particle is aligned in a certain direction. Let's say it is this direction. I draw two extremes. I draw two parallel lines at two extremes, and the distance between these two parallel lines is called the ferret's diameter. And if I want a Martin's diameter, what does the Martin diameter do is it will divide your particle into equal halves. So you can do that in images software also. So you divide this, and then you find out the average diameter. Okay. So, and this also will give you the particle size. So it will count, and so each particle will have certain diameter, and it will average out, and it will also give you standard deviation. So that is about how do we do how do we find the particle size in images software after getting the images from SEM. Now, that is about receiving. And there are industrial screenings, and the industrial screenings have some certain feed rate, okay, and certain size of aperture, and certain size of no, oh, that's all. So you have feed rate, aperture, and there is also this vibration, right? So you can even have dry screening. There is also wet screening. It depends on whatever equipment you are trying to use. So what are the different things that affect this screening? Are the particle size, obviously, because that's what we are trying to separate them, right? And then you have feed rate, the amount of feed that you are trying to give, and also the screen angle. See, the screen angle will also depends, right? So suppose you have a very flat, right? This is your screen angle. Now if you maintain it like this, okay, it also defines your sorting, okay, and also the amount of vibration, moisture, amount of moisture, because whenever you have moisture, let's say you have a moisture on your surface, then if for example certain particles are just below that size, okay, then what happens, because of that moisture they stick to that aperture, and they block, and they worsen that state, because no other particles can go through there, so it is completely wasted, right? So again, so that's why whenever we are trying to do sieving, there is a standard. So first we dry it, then at for certain temperature, then we use the sieving process, right? So there are different screens. There are rotary screens, roller screens, the Bradford screens, which is very like old one, and there is the terminal screens, right? So it depends which type of industrial equipment they are using. Okay. Now that's all about the powder particle size estimation and screening. Now moving on to the fuels in metallurgical process. Okay, what are the different types of fuels that we use? For even for pyrometallurgical process, if you need energy, right, to do any type of process. Right? Even for screening, you need vibration. Vibration comes from electrical energy. And electrical energy you have, then you need to burn something. Right? So, and for metallurgical process, for mostly for pyrometallurgical process, like for example in steel making or iron making, there are many things that need to be taken care of. You need to do first sintering. You for sintering you need thermal energy, and thermal energy comes from fuels we use, and there are different types of fuels: solid fuels, liquid fuels, and gaseous fuels, and also depends upon type of material you are working on. Okay. Now, so let's define our solid different types of fuels, right? Initially, solid fuels. So fuels, solid fuels, liquid fuels, gaseous fuels. So for solid fuels, we know the most basic fuel that has been used from like past centuries is the wood or coal. And liquid fuels, you have diesel or industrial grade metallurgical fluid fuel. And gaseous fuels, you mostly use methane, the hydrocarbons, right? Those are the most uh, basic type of fuels that we use. Now, before choosing any type of fuel, we see certain factors, right? So, what is the amount of energy that fuel is giving while it is burning? So that is called as calorific value. Calorific value is nothing but the amount of energy that is generated by burning a certain volume of fuel. Okay, so there again in fuels there are primary fuels, secondary fuels also, and there are different types of analysis. We use proximate analysis, ultimate analysis. Okay, now so again fuels are sources of heat. So fuels are sources of heat energy, right? Now let's the fuels are different, right? You have solid, liquid, and gaseous. See, in solid fuels you have wood. So wood was still used in copper few years ago in some furnaces for refining of copper. So right, we still the people had still used wood to refine, not normal wood. So liquid, you have crude oil. So you might have petrol, diesel, so on, right? So from wood you can get coke. So you actually get coal, then you do some process, destructive distillation, then you get coke. Coke has higher calorific value when compared to coal. What we do is in this is called as a coking process. Coking process is nothing but you heat the coal, you remove the volatile compounds, volatile matter, whatever is there. So and even remove the moisture also. So you take out these things, and at first it will become soft at some 400 degrees centigrade, and once you reach 600 degrees centigrade, again after removing everything, after our impurities going out, it will become hard mass. So that is called coke. Okay, So that's why we call this coking process, people call it destructive distillation. Destructive distillation process, right? So that is what we do. Now, in gas, you have hydrogen gas, okay, and also you have hydrocarbons, right? Now, this coke, whatever we get, is coming from bituminous. See it whenever a wood or any organic compound uh, trapped inside earth, and because of continuous sedimentation, so because of the pressure from the earth's surface and the temperature, all the environment will result in the compression of this wood. Okay, so this wood will first become peat, then it will become lignite, then it will become bituminous, then it will become anthracite. This has the highest calorific value, okay, and followed by bituminous, then lignite, then peat. Maybe this peat comes, lignite comes first, then peat maybe. So I have to check. Okay, so this is how it happens. Now, so that is about coke. Now, depending few, so the most basic metallurgical, I mean the most important metallurgical process, metallurgical units that we see are the BF, a blast furnace, and the BOF, which is the basic oxygen furnace. So these are the two. Uh, if you have an integrated steel plant, then basic, I mean the blast furnace and basic oxygen furnace are at the same place. So the blast furnace uses coke. It is a counter current. That means the coke and the ore comes from top. The air is comes through the bottom. Okay, so that's why we call it as a counter counter current process, because one is going down and one is going up. Okay, so air is blown from the two ears. So two ears are like this, and this comes from top. Okay, so while coming from top, the carbon will react with air, will form gases, the carbon monoxide, right, and it will reduce iron while coming from top to bottom, and everything is happens in a certain uh, system, and that is called as blast furnace. And then you have basic oxygen furnace. You have very big ladle. Then you take the pig iron that comes from it, from a blast furnace. Why we call it as a pig iron? Because whenever we solidify, it forms the face of pig. I mean, in later stages, that's why they call it as a pig iron. It contains approximately 66 to 68% of carbon. That is huge for steels. So you want to remove it. So what you do is you apply, you just blow oxygen into this steel. Yeah, people might ask, so just you reduced, then why you are again oxidation? So at that temperature, the oxides are not very stable, and also the impurities will oxidize first rather than your steel melt. So then you blow oxygen to an extent that you form a froth, and there are different things that happens. That is basically the steel making technology. We are not going to go deep into that. Now, after a certain point, you stop oxygen. So then you take out the steel. Okay? So that's what happens. Now the fuel here is, the first is coke, right, and air, obviously. Now that is for steel making technology, right? And for DRI, there is a non-coking coal. There are direct reduced iron. So that is one thing. There are other Corex process, and in aluminum industry also we use non-coking coal for power. Now, Copper extraction, we use diesel to heat, right? The liquid fuels, if you're talking about the secondary fuels, we use diesel. Okay. And yeah, so that's what we do. Now, uh, again, coal characteristics, yeah, so it is first wood, then peat, then lignite, then bituminous, and anthracite. That means the amount of oxygen content goes down, the amount of carbon contents goes on increasing from peat to anthracite. So that's what happens. Now there are different ways we do the fuel characterization. So fuel characterization has, we do some analysis, and also we do with the calorific value. So when we are talking about any analysis, so let's say if I'm talking about proximate analysis, right? Then the coal has how many compounds? One, that is carbon. So carbon, and you have hydrogen plus uh, phosphorus, right? And there is sulfur. So these are the things that we get, right? So that means some is the volatile material, some is hash, and some is fixed carbon, right? And the some comes from mineral matter. Okay. So let's move on to the next point. Now, how do you define this, right? So you have inherent moisture, the moisture that is normally trapped whenever you put some, if you have some hygroscopic compounds, so they trap moisture. So that is common. Now, how do you know the amount of moisture is there? So what do? You do heating up to 110, 115 degrees centigrade for 1 hour. Okay, this is standard process to remove the moisture. And if you want to remove the volatile matter, now you heat up to 950 to 925 degrees centigrade for 10 to 20 minutes. Then volatile matter comes out. So then you measure the weight. You know how much of amount has been lost, right? Now during this heating, there is also some H present, hydrogen present, and some oxygen might also present there. And this hydrogen and oxygen also will react. They will form water, right? And you are heating this water to become steam. So that part also needs to be considered, right? Because some amount of energy is also going into heating steam, right? And also in changing the water from liquid to gas, right? So that is also needs to be considered. And there is our ash, ash percentage. Now ash percentage is defined by you first heat your coal in air. So everything, these thing happens in most of like absence of air, right? So this thing happens to remove alternate matter, it happens in absence of air, or otherwise your coal will get oxidized. Now to know the ash concentration, so you heat it at 450 degrees centigrade for like 30 minutes, right? So all the carbon, sulfur, right, will get, sulfur and part of the carbon will get oxidized. Okay. So this sulfur can be found with, if it is a nitrogen, also nitrogen can be found from Geldal method where it is converted into ammonia. So this amount of conversion will tell you how much of nitrogen has been produced. And if you want to know the sulfur, you do oxidation, then you will have sulfur SO2 or SO3. Then you react with your alkali, which is the most, I mean, reasonable alkali will be barium. Then it will form barium sulfate. From this, you know amount of sulfur is there. Okay, that's about that. Now heating at this will remove the sulfur, and oxidizing again, increasing temperature for 1 hour, right? It will oxidize all the carbon. So then finally you will have the ash percent, right? Okay, so that is about that. Now there are a few formulas, so they are straightforward. So I'm not going to derive them, right? And there is an energy and environment factor. What type of fuels you need to use? What are the byproducts from those fuels? So how do you make sure that you are not degrading the environment? So what are the steps that needs to be taken care so that we are not like our byproducts are leaving to environment, right? So whatever the sulfur dioxide or SO3 that we get by oxidizing, if you have seen integrated steel plants, wherever you have this coking factory, that means wherever this coking equipment is there, at far you will also find the sulfuric acid plant also, because during coking you will get sulfur, and that sulfur is your sulfur dioxide, and that sulfur is when further oxidized, right? SO2 plus O2 plus SO3, and then it is reacted with your water, it will give you sulfuric acid, right? So this is the famous reaction, and there are different. The famous reaction has a name also. So that's how you get whenever you have integrated steel plant or iron making plant, then you will find the sulfuric acid plant also. So that's how you reduce the byproducts that you are getting, and also when you sell sulfuric acid, you will have some economical thing also. So that's how you are getting some byproducts, then you use them, right? So instead of just living to the environment, which is bad, right? So that's all for today's session. Now let's move on to the problem solving part. Okay. Okay. So now, see, in sedimentation, what do we use? So sedimentation mostly depends upon the gravity, right? So just a revision, okay? So sedimentation will depend upon your gravity, and gravity does the most of the work. So it depends upon your size, your density, density of solid, density of liquid, and also the medium in which it is, and whether it is a turbulent or Reynolds number. So it depends upon Reynolds number, turbulent or lambda, right? And if you are talking about froth flotation, okay, so if I'm talking about froth flotation, uh, what do we use? So froth flotation depends upon the surface properties. That means the wettability, and that in turns depends upon the surface energy. Right? So these are the things that defines your froth flotation. And collectors, we have seen xanthanates, right? Mostly we have seen people using them. Now again, the paramagnetic. When we are talking about the magnetic field separation by applying magnetic separation, we defined our materials. We have different materials, right? You have paramagnetic materials and diamagnetic, right? So we have different types of materials. Right? Now, so paramagnetic materials are not the susceptibility is less than 1. For diamagnetic materials it is less than 0, which is negative. So for ferro, susceptibility is greater than 1, right? Very large. So when you apply magnetic field, they will give a fast response because they have inherent magnetization, right? So that's what happens when something has inherent magnetization. It will give a fast response to your magnetic field, right? So you do not need to apply a very high amount of magnetic field, so that's why you use low intensity magnetic field to separate. Now what about paramagnetic materials? Because of the susceptibility less, they need a strong magnetic field, right? So the force on a magnetic particle, right, it depends upon the B, or you can say the amount of flux density that I have been applying, and also it also depends upon the del V, or you can call it as a gradient of B. So even if you increase the B from like 1 Tesla to 2 Tesla, the response is small. But if you have a large gradients, right, even if you apply small magnetic fields, if your gradient is large, that means dou B by dou X is large, then your paramagnetic materials can be attracted to them, right? So that's the basic difference. So that's why we have low intensity, high intensity, low gradient and high gradient magnetic separation, because of this paramagnetic particles, right? Now again, so what does X-ray uses? They depends upon, they use atomic density, right? X-ray use atomic density. Gamma rays again happens via fission reactions. So some atoms will break and form two atoms, and that with those two atoms there are some other particles that will be released. So they can be alpha particles, gamma, beta, right? It depends on what type of atom it is going. For example, if you have uranium, so whenever a uranium splits by bombarding a neutron atom, it will give you one and half, 1 to 2 neutrons, depending upon fission. Right? It's more probability way, so that's why we call it as a half, right? So the average value, value of neutrons that each fission reaction of uranium produces is half neutrons. So it's a probability, right? Sometimes it can produce one, sometimes it can produce two neutrons. It depends upon what are the byproducts that are getting, right? And when you have extra fluorescence is nothing but you emit some wavelength, it will give you some wavelength. Okay, so lambda 1 and lambda 2. So every atom will give you different response. So that's why you have fluorescence. And then yeah, so again I have mentioned coagulation. Whenever during coagulation and whenever a particle moves, so there is a shear between layers, and the shear plane, the charge of the shear plane is called as a zeta potential, right? So that potential should be zero for effective coagulation, right? And more free agglomeration, free and spaced agglomeration can be seen in flocculation because of the use of polymers, right? So that is one thing. And then chelation is nothing but right, so you have chelation. Chelation is nothing but forming multiple bonds, okay? Just like a carbonyl, metal carbonyls, they have 4 bonds, they form 4 bonds with metal carbon. Certain vanadium, chromium, they form 4 to 5 carbonyls, okay? So that is one. And now magnetic drum separators, they have a magnet, right? North south, so they have magnetic drums, so the powder particles will get attracted, right? So that's why they call it the drum magnet separators, drum magnetic separators. And then you have induced magnetic separator, that means you have a drum and then you apply a magnet. Let's say these are north and south, that means you are inducing magnetization in a drum. So that's why you call it as an induced magnetic roller. That is one thing. And then cross belt. So what do I mean by cross belt? So that means one belt carries some material, feed. So for example, feed material. So it is carrying feed material. It contains both A and B. So a cross belt is put besides on your feed main belt. So this belt is magnetic. So what it does is it takes out. So let's say A is magnetic, okay, B is not magnetic. So A gets attracted to this belt and it flows here. B will not get have no reaction to the magnetic field, so it comes here. So that is about that. And then you have permanent magnetic role, right? So nothing but you are having a permanent magnets. Okay. So right. So that is about that. Now, yeah, I have explained, right. For microscopy, we mostly use ferret number because that gives better average value when compared to your Martin's number, right? Whenever you are talking about when sedimentation and Stokes law, then comes the Stokes diameter, right? So and yeah, so that's all for the today's session, right? I have discussed most of the questions and I have explained more, I mean, the important theories that might be asked in as a questions in exam, right? So that's all for today's session. Right? Okay, if you have any doubts, you can leave here. If you do not, then you can. So if you have any doubts, you can stay, or if you don't, you can leave. Before that, let me stop the session.